Okay, so we'll start our lecture now. Um, Previously, I gave a question that was to find out the complexity when our recurrence relation is t of n when it's equals to 2t of n by 2 plus n. So let's try to find out the complexity for this. Um, First of all, uh, I'll substitute the value of n by 2, t of n by 2. What I'll do is substitute the value of t of n by 2 in here. So what I'll get is 2 into 2 into t of n by 4 uh, plus n by 2 plus n. Are you clear with this? That the value of t of n by 2 will be equal to this. You got this point? Or do I need to explain it? You got this point, or do I? Okay, let's find out what's n by 2. We'll just have to provide n by 2 here, right? That will be equal to 2t of n by 2. That will come to n by 4. Now n is also substituted by n by 2. This is the value of t of n by 2 that's happening over here plus n. Are you clear with this? Am I audible? Okay, good. So what we are doing is, for this particular recurrence relation, when t of n is 2 of t n by 2 plus n, what I'll do is to substitute the value of t of n by 2. What will be the value of t of n by 2? I have to substitute the value of n to be n by 2 here. That will be equal to 2t n by 4 plus n by 2. That's what I have written here. Then the simple t of n function. Resolving this, this will be 4t of n by 4 plus 2n. That will be 2 multiplied by n by 2 n plus n. That's 2n. Again, if you put out the value of t of n by 4, what you will get is 8t n by 8 plus, sorry, not 4 of n, 3 of n you will get. You will get 3n. Proceeding further, if you'll put k, you will get a value that is 2 power k t n by 2 power k plus k of n for some kth from some kth operation. So now what I have to substitute is this, the value of t n by 2 power k with the base condition. Base condition, okay. So for every of the case, every of the question, I'm assuming that the base condition is 1. That O of 1 is 1. This is my base condition. Now, let's say I'll substitute n by 2k is equals to 1. So now I have to find the value of k. N by 2k is equals to 1, then k will be equals to log of n, log base 2 of n. Try to solve this, you will get that. Now k is log n. I'll put the value of k in this particular equation, right? What I'll say is that it will be equal to uh, 2 power log base 2 of n plus t of n by 2 power log of n plus, that's k into n. I can say it is to be n log n. So it's equal to solve. It's your home. Try to solve out this equation. It will come up to n log n in big O notation. These two will will be asymptotically smaller, as I have already discussed that we ignore the smaller order terms. We will just have this over here of n log n. Similarly, for t of n of 2t n by 2 plus 1, what I'll say is that I'll put the value of t power n by 2, t of n by 2. What I'll get is 2 t of n by 2. That's again 2 into t of n by 4 plus 1 plus 1. So that's 4 t of n by 4 plus 2. Going ahead, if I write it in the form of k, that's 2 of n by 2k plus k. 1, right? Okay, cool. So now you have to substitute the value of n by 2k to be 1, and you have to again now solve it. Now this is your homework. That's the main logic I have written. Now that's your homework, that if you'll put n by 2k is equals to 1, then what will this solution will reduce up to? I'll tell you the answer, that it will reduce it to O of n. Try to find out this result. The answer for this one was again O of n, and answer for this is O of log n. So try to find out the complexities of this. I have already discussed one, the partial 2, and for 3 and 4 you have to find it out. Okay, so we will proceed further. Let's say okay, we will discuss the simplified master's theorem first. Simplified master's theorem. Now what simplified master's theorem does, what it says is that if we have a recurrence relation, by just saying it and finding some of the relations in the particular variables we are having, we can find out what can be the complexity for that recurrence relation. Okay, so this particular simplified master's theorem will work only for some particular recurrence relation. It will not work for everyone. So this is the first drawback, or else we could have used the simplified master's theorems and everything. So it will work for only of the recurrence relation who are of the type, or can be reduced to the type of t of n is equals to a multiplied by some t of n of b plus some function of n. So if any of the recurrence relation is in this type, I can say that I can apply the master's theorem on this. So now let's say I have a variable t that I'll find it as log of base b to a, and my function of n should be n c. We have to find the values of c and t, and accordingly there are some logics from which we can directly deduce the algorithm, the complexity. So let's say if after finding the value of c, after finding the value of t and after finding the value of c, there can be three cases, right? That T is less than C, T is equals to C, T is greater than C. If it is less than C, my complexity will be n square. In this case, my complexity will be n log n, and in this case, my complexity will be n par t. So this is the master's theorem. I'll repeat it again, that any of the recurrence relation that is in this particular type, that is A multiplied by T of some n by B plus some function of n, will find the value of T as in log B A. We'll put the function n is equals to n power C, and we'll try to find out the value of C. After finding out the value of T and C, these three can be the cases we have, that either T is less than C, T is equals to C, or T is greater than C. If my T is less than C, my complexity I can say directly that it will be n square. If T is equals to C, I can say that's n log n. And if T is greater than C, I can say that my complexity is n par T, whatever the value of T will be. So let's try to do some question over here so that it will be clear to you. Let's say I'll take this particular example again. That was 2Tn by 2 plus 1, right? So A, T, n by B plus some function of n. This is in this form, in the form that we are looking, right? So I'll say that my T of n is 2T n by 2 plus 1. So now I have to compare it with this particular thing, this particular formula I have. So now my A is 2 in this case, my B is also 2 in this case, and my function of n is just 1. So what I'll say is my A is 2, my B is 2. So now the formula for calculating T is log B of A. I'll say log B of A. The value, I'll insert the values log 2 of 2. It is equals to 1. Okay. So now my function of n is equals to 1. I'll equate 1 is equals to n par some C. So putting n par 0 is equals to 1 for any of the value that's n. If I'll have a power 0, then only it will equate to the result 1. So my C is 0. So now in this case my T is greater than C. My T is greater than C, right? T is 1, C is 0. T is greater than C. Let's go and find out what's the case. Less than C, equals to C, T is greater than C. What I'll say is O big O of n par T. Now the complexity for this is O big O of n par T. What's the value of T? It's 1. So that's n power 1, or I can directly say it's O of n. You understood this question, or do I need to repeat somewhere? Please note it down. If you have any questions, please ask. Okay, so I'll take one more question. I'll take the first equation as well. It will be more clear now. So let's say The first equation was t of n is 2t n by 2 plus n. Again, my a is 2, my b is 2, my t will be equal to 1 only, again in this case. Now my function of n is n, right? Now for this particular n, I have to equate this to n power c. Now when n power c can be equals to n, only and only when only and only when c is 1, c is 1, right? So now in this case my t is equals to c. What I'll say that I'll go up. I'll say if t is equals to c, my complexity is O of n log n. So my complexity is O of n log n. So we have discussed three types to find out the complexity for a recursive approach. First is recurrence relation. What we'll do is to reduce the complexity by providing the value of t of n minus 1 or n by 2 in the particular equation, and we will find it till the k. Then we will substitute the base condition, and then we will fetch the value of k and put it in the equation, and then we will get our complexity. Second part was a recurrence tree, in which we will go order by level by level. So in every of the level, I'll count the number of function calls. After everything, after the tree is made, I'll count the all the number of function calls in all of the levels. The sum of this will be equal to my complexity. Third is Master's theorem, that will use your recurrence relation, that is of the type a t n by b plus function of n. Here are the two questions for this. Please note it down and let me know once you're done, then we'll proceed further. If you have any questions, please ask. Okay, cool. Um, if you have any questions, please ask, because this Master's theorem is important and we will be using it further to directly write out the complexities for any of the solution approach we are writing. So let's deep dig the recursion. We'll do the very famous problem, that's Tower of Hanoi. Tower of Hanoi. What is it? I have a source. Do anyone remember what Tower of Hanoi is? Maybe no. I have a source. Okay, cool. I have a temp and I have a destination. Let's say there are some n number of tiles. We'll take 3 for the example. I have a bigger tile, smaller tile than this, smaller tile than this. What I have to do is to shift it to the destination, considering the point that at any given point of time, my smaller this smaller desk cannot be below of a bigger desk. So we have to use this temporary pole to shift all of the end decks to the destination pole. Can you write me the solution? Just the solution for this. What will be the solution for n equals to 3? Let's say my source is A, my temp is B, and my destination is C. How will you proceed for this? Take 2 minutes of time. Take a pen paper and try to find out how will you do this. Okay, we'll proceed. So what I'll do is to uh, first of all, let's say this deck number is one, this deck number is two, this deck number is three. What I'll do is to remove this one from source and I'll put it here. Then I'll put the second here. Now I'll put this back again here. Now in here only 3 is there. It is empty. I'll put 3 here. Cool. It is removed. Now I have two elements over here. The biggest deck is on the destination. We will not touch this now. What I have to do is now, this is my, now at this particular moment, this is my source because every of the desk we are using is here. This is empty, so this will become our source and this will become the temporary, and the destination remains the same. What I'll do is to take the smaller one and put it here. Now the smallest one is here, the second one is here, the third one is here. I'll take this second one and put it over here. After that, the small was here, I'll put it here. So all of my three tiles are shifted here with the condition that at any given point of time, the bigger desk was not above the smaller desk. Are you clear or do you have any confusion over here? Okay, I'll write down the steps as well. So firstly, what I did is to take the first desk and remove it from A to C. Then I took the second deck and remove it from A to B. Then I took the first deck again. Then I shifted it from C to B. Then I took the third deck and shifted it from A to C. After that, A is in the C, 3 is in AC. Then I did is I took the first deck and removed it from A to B. Then I took the second deck, I removed it from B to C. Then again I took the first deck that was on A and shifted it to C. Are you clear now? So there are total 8 number of steps. So for any of the n given, the total number of steps will be 2 power n. Are you clear? Sorry, it will be 2 power n minus 1, right? Yeah, that's 2 power n minus 1. My bad. So for any of the given n, it will be 2 power n minus 1. Are you clear with the solution for 3? Then we will write down the code for this. Are you clear with the solution? Okay, cool. So now I'll write down a function to print this particular statements. These particular statements for any given n. Any of the given n. What I'll do is I'll have a function void tower of Hanoi, and in which I'll do is to take the n, the number of decks I'm having, my source, I'll take it as char src temporary and destination. In our case it is A, it's B, it's C. I'll write down the function. So now the very first thing is to assume that the star of Hanoi function is working as expected. Then only we will be able to write our code efficiently and fastly. Now the very first thing is what I did is that my main goal for first step was to put this 3 to this D. That was my goal. For this particular, I have to remove this 1 and 2 from this one to this one. That was my whole goal for this particular tray. for this particular deck 3. What I did is that I removed this 1 and 2 to the temporary using destination. I put the first on the destination first, then I put the second on temporary, then I moved it back to the temporary. I used the destination as a temporary for shifting 1 and 2 to this particular temporary, and this was for this particular instance that worked as a temporary, and this worked as a destination. I reversed the role. Are you getting what I'm trying to say? That for first two deck, the destination was the temporary and temporary was the destination. I reversed the rule. Then when I'm having both of them here, I remove 3 from source to destination. What I'll say is, I'll write the base condition after writing the main logic. What I'll say is that my first goal is to take n minus 1 elements from source to from source using destination to temp. That's what I did. I'm assuming that this particular TOH function, tower of NI function, is working as expected. If I give a source, a temporary, and destination, it will put all of the n decks we are having from source to destination using temp. So now what I did is that I removed n minus 1 decks from source to destination using temp. Is that cool? You got till now? So now I'll say that I have to remove the nth deck from source to destination. I'll just say that print n from source to destination. Now again, what I did is now my third one was here, my other two was here. Now I have to do is to, from the temporary one, there are two, here is the third deck, I have to shift this to here. That's what my whole goal is. So what I'll say, using the source as temp. So now the temp will become my source, this will become my temporary, and this will remain as my destination. And this, the role reversal is for source and the temporary. Previously it was for the temporary and the destination. Tower of Ni of n minus 1 elements. My source is temp, my temp is source, and my destination remains the same. Now I'll write down the base condition I'm having. If I reach n is equals to 0, I'll just say return, that we don't have to do anything over here. Are you clear with this code? Okay, I'll write down the recurrence tree for this, maybe then it will be more clear. So my initial call was, let's take that example 3 ABC. My n was 3, my source was A, my temp was B, and my destination was C. This is my initial call. Okay, so after this, when I call this, I have two function calls, this function call and this function call, in which first destination and temp is getting reversed, and the second one source and destination is getting reversed. I'll go one by one. So what I'll do is n minus 1 source and destination and temp. So I'll say that I have called to n minus 1. In here, my temporary and source reverse their role, C and B. So now when I have called this, I'm here 2, A, C, B. Now I'll check if n is 0. No, it's not 0. So I'll come again, I'll call again. what I'll do is to call it again, with again my roles being reversed. So now again in this particular, the C and B will reverse each other. 1, A, B, C. Now it will call the 0, 1. It will again call and it will return nothing, because at 0 I'm saying just to return and do nothing if n is 0. Now for this particular, I have called this function. Now I will say that print function will be called. So it will print 1, as it is 1, from source to destination. In here, my source is A, destination is C. From A to C. Cool. After printing, it will call the second half with my source and temporary being reversed. So it will call one of C, A, B. After one CAB is called, it will call the 0, 1, and this will not be giving us any of the result. As for 0, there is nothing. I mean, sorry, for 0 there is just return. So now our function call for this is done. So now this will print out. Okay, so when it has called 0, it will go for the print function. It will say 1 from C to B. This, okay, sorry, my bad. Before calling this one, it will also go for the print function. It will print, I'll write down the sequences as well. The sequence 2, that it will print 2 to A, B. Now this is my third print statement. So now from here I came here, from here I came here, then print function called, then again it will call 0 and it will return nothing, right? I came here, then I came here, 0, that will return nothing, that will then print, then it will again call for with the 0 and with the other elements, it will return nothing. Now I'll return from here as well. So now this function call is completed. This will return. After this left part is returned, this will go for the print function. It will print 3 A C. That is my fourth print. Now I'll go to the right half. In here, what's happening is source and temporary are getting reversed. Just a second. In here, source and temporary are getting reversed. Source is A, temporary is B. B, A, C. Now it will again go for this 1. Again AB will tick each other. They will reverse each other. Now it will call for 0. It will return nothing. Then it will go for the function print. The fifth print will be from okay, for 1 Week2 C. This for this print is from this particular function. Again it will go for 0 and will return nothing. So now this function call is completed. This function call is completed. This print statement is also done. What I'll say is to go here back. Now this will go for the print function. This was my fifth print. Sixth print will be 2. It will go from B to C. Now it will go for 1. It will have the reverse again, the A and B again getting reversed. It will go for 0. It will return nothing. It will go for the print function. That will be my 7th print. That will be from 1 of A to C. Then it will go for the right function. It will return nothing. Now this function call is completed. It will go here. This function call is completed. It will go here. So now, while we were doing the recursion, these all statements will get printed. 2, 3, and then this fourth, then this fifth, then this sixth, and the seventh. It's a bit tough to understand. Please take your time and try to look over here that how it is functioning. Okay, first note this code down. Note this code, and then we'll look into it. So according to this code, this particular reference tree, please note this down as well. This is a bit tough to understand. If you have not received it 100%, no issues. Try dry running this code once or twice or thrice, you will be able to get it. Should I proceed further, or do you want me to repeat something? Should I proceed further, or do you want me to repeat something? Guys, please respond. Okay, cool. So now, let's say I'll write down the power function. The last tower of Hanoi is bit difficult. Please try dry running it on your pen paper once or twice, or else you will not get it. So now we'll proceed to the power function. So this power function, what it will do is to take some int a and int b, and what will it will return is a power b. That's my goal. That is what my goal is. So let's say again, what I'll do is that first thing is assumption, is an assumption. Second thing is my main logic, and third is my base condition. Now, for any of the power, let's say a power 5, I can say that it will be equal to a into a power 4. Can I say this thing? Guys, please respond. Can I say this thing that a power 5 is equals to a into a power 4? Okay, cool. So for a power n, let's say we are having a power b. For a power b, I can say that it is equal to a into b minus 1. That's what I'm going to do. I'm assuming that it will be returning me the value of a power b minus 1, and will just multiply with it a. I'll say return a multiplied by uh, power of a b minus 1. And in case my b reaches 0, I'll say return 1. uh, are you able to get this is my assumption, this is my main logic, and this is my base condition. What I'm doing is to just multiply a with the power of a b minus 1 for any given b. You got this code? Okay, cool. Let's try to find the complexity for this as well. I'll take an example. Let's say I have to calculate 2 power 3. Let's say I'll call the function 2 power 3, 2 and 3. What it will do is it will call 2 and 2. Just a second, I'll put my Mac on charging. Okay, so it will call 2 and 2. It will call 2 and 1. It will call 2 and 0. So now when my b is 0, what I'm saying is, that's my base condition here. If my b is equals to 0, return 1. I'll say return 1. Now my 2, 1 will say 2 multiplied by 1. It will be returning 2. This will be returning 4. And now when I have returned 4, that will be multiplied by 2, and my final result 8 will be generated. So this is my recursion tree for example of 2, 3. So it does that is not mandatory for the Fibonacci. We got 3 sub branches for every of the sub problem, and this for every of the sub problem we have just one branch. So the total complexity for this will be the depth of our recursion. This is also known as depth of recursion. The depth of the recurrence tree is also known as the depth of recursion. So now how many levels do we have? It is equals to b plus 1, sorry. The number of levels are b plus 1. B plus 1 levels we have. Or else I can say that my complexity is b plus 1. That is equals to O of b. Or if you are not very familiar with b, I can say that rather than b I'm taking n, and for here this complexity will be of n. Okay, you got this till here, or do you have any confusion? How is the leveler coming to be b plus 1? Isn't it 3? Uh, this is for 3, 2, 1 and 0 as well. We are calling for 0, right? Okay, good. Okay, so what we did is that we said that a power b, this a power b is equals to a into a power b minus 1. And this is how we wrote our logic. Let's say I divide my a power b in some other way, not this way. I'll try to optimize it. Can I say that let's say my a power 6 is equals to a power 3 multiplied by a power 3? Can I say this thing? Can I say this thing? Cool. Let's say my a power 7. Can I say that it's a into a power 3 into a power 3? Okay. So what I'll say that if my, let's say this is n. If my n is even, then a power n is equals to a by 2, n by 2 multiplied by a power n by 2. If my n is odd, I can say that a power n is equals to a multiplied by a n by 2 multiplied by a n by 2. Can I say this thing? Are you clear with this? Yeah, good. So now let's try to write down the logic according to this. What I'll say is that again I have some power function that is taking some int a and int n that will reduce the result of a power n. So let's say in any of the condition, if it is even or if it is odd, I have to somehow calculate a n by 2. Doesn't matter, I will be using the value of a n by 2 in both of the cases. So what I'll say is that I'll save this in some temporary variable, and I'll say power of a comma n by 2. I'll save this value. Now what I'll do is that I'll check if n mod 2 is double equals to 0. That's a check for even or. Yes, if it is even, what I'll say is return. What I have to do is n by 2 multiplied by n by 2. My a power n by 2 value is stored in temp. I'll say return temp multiplied by temp. Else return a multiplied by temp multiplied by temp. And now this was my assumption that power of a n by 2 will give me the result. This is what I am assuming. This whole is my main logic. Now I'll come to the base condition that if my n comes to be if it comes to 0, I'll return 1. Are you clear with this code? Do I need to repeat, or are you clear with this code? If you are clear, then we'll try to find out the complexity. Are you clear with this code? Okay, sorry, I missed that. Okay, now let's try to reduce the complexity for this. For any of the Tn, what I'm saying is that there is some constant operation of the space condition. After that, I'm having T of n by 2, T of n by 2. After this, there is no function call. We are just using this temporary variable as it is. There is no function call at all. So my T of n is equals to 1 plus T of n by 2. We already solved it, that if my T of n is equals to T of n by 2 plus 1, my the time complexity is O of log n. We have already solved this recurrence relation. So now, just by changing the type of the subproblem from this to this, we reduce our complexity from O of n to O of log n. You understood both of the codes? If you have any doubt, please ask. We already reduced this recurrence relation of t n by 2 plus 1. I'll show you. T of, okay, I have not done this. This is your homework. This will be equal to log of n. Once you solve this thing, you will be able to get this. That's actually your homework to find out that why it is equals to log n. Okay. Yes, but how this t of n has come from the school? Okay, cool. We'll discuss it again. So for any of the tn, there is some base condition that is taking some constant time. This if else is also taking some constant time, right? In this particular, there is no other function call. We are having a function call over here in this for, and we are storing it in the temp, and this is our function call. In this, I am not having any of the function call. This is a constant time operation. So I'll say 1 plus, I am saying power function of a n by 2. So this will take the time required for calculating n by 2 elements. T of n by 2. Cool. Please note this down, then we will proceed further. Then we'll proceed to backtracking. Okay, so shall we proceed? Guys, shall we proceed or do you have any questions? Okay, cool. So now we'll proceed to backtracking. Backtracking. So now, what backtracking is? What we do is to that we have, let's say, we have some certain amount of input and we have some certain output, or we have to check that if there is some particular way to reach somewhere. What I'll do is to I will find out recursively for every of the solution. Let's say I'm at some position. At any of the position given, I have four options to do. Let's assume that we are into some case in where at any given point of time, if you are at any particular position, you have four options to choose from. What I'll do is that I'll choose the option 1. For this option 1, I'll say I'll choose all of the options one by one. For this option 1, I'll choose option 1. Then when I backtrack, I'll choose option 2, option 3 and option 4. So what I'll do is that I'll recursively call for option once. Once I reach a level where I say that this particular option is failing, I'll backtrack and I'll go to option 2. For this option 2, I'll call for option 1, 2 and 3. Recursively, I'll call out the options at every point. I'll call for the recursive options, and while once I reach a level where I know that this particular approach is not working, I will backtrack and I will choose the another option. This is backtracking. Till now, what we are doing is to just keep recursing on, and we will just multiplying or adding some particular bits over here. Now, in till now, what we did is that every time we were having just one option to let's say if we were finding some natural numbers, every time I'm just adding it up. For every recursive call, I'm adding. Now, let's say I have four options. For every of the case, I'll choose all of the four options recursively and will find out that if there is something that is working out for me or not. Let's say we will do a question where I'm given an array. Just a second. So I'm given an array of n length. Let's say it's 3, 1 and 5. My k is equals to some value, let's say 8. What I am supposed to do is to find out that if there is any subset whose sum is equals to 8. I have to find every of the subset that's whose sum is equals to 8. In this particular, there is just one subset. We will just try to find out every of the possible subset now. So now what I'll do is that let's say first of all I'll consider this subset, a null subset. Now I will take 3 into the consideration. I have two options for a subset to be generated. I have two options that either I can include it or either I can exclude it, right? For any of the subset, I can have just two options here. What I'll say is that firstly, I'm including it. Secondly, I'm not including it. Now, what I'll say is that I have -1 now, or 1 or minus. I have 1 now. What I'll say is that I'm including this 3 and 1, and I'm not including this. If I'm including this, that's 1. If I'm excluding this, that will remain null. Now I have 5. So for every of the level, I have again two options. I will include 3, 1, 5. I'll exclude 3 and 1. I'll include 3 and 5. I'll exclude. Again, I will include this. I'll exclude this. If I include this, I have 5. If I exclude this, this remains null. Are you clear with this subset generation? Are you clear with this subset generation? That at any given point of time, for any of the element, I can have two options, either to include it or either to exclude it. I took 3 first, that the first element first. I included it. In this case, I excluded it. Now I'm taking 1. For both of this, I have to take 1, right? So in this case, I'm including 3 and 1 is my subset. In this case, just 3 because I am excluding the 1. In here, if I am including 1, my subset will become 1. If I am excluding, it will remain null. Same for every of the other call. I'll take 5 for this particular level. Um, are you okay to go for the code? Are you clear with the subset generation? Okay, I'll proceed to the code. Let's say I'll write down the code. Let's say my current result is 0, that there is no subset as of now that I have found that gives me the value of k. This is my global variable. I'll say that I'm writing a function, that's a void function, that says that I'll take the array, I'll take the n. So now n is the length of this array and int k. This is the sum that we are finding. This is the sum that we are finding, and is the length of this array. So now, what else I have to take? I am taking this values one by one. Firstly, it was null. Then I took the first element. Then I took the second element. Then I took the third element. So I have to maintain some index that at any given point of time, I should know that which element I have to pick next. At this point of time, I should know that I have to pick the third element. So I have to maintain some index. Correct? Now, at any given point of time, when I am generating the subsets, I will for every of the subset, I'll check that whether it is equals to 8 or not. Whether it is equals to 8 or not. If it is not, I'll not do anything. If it is equals to 8, what I'll do is to increment this result. Cool. So I have to get this sum as well. Are you clear with the parameters we are having? I'll write down the code, then it will be more clear. So now, again, it's a recursive call. So at any given point of time, what we were having, either to include or to exclude. These two calls we were making, right? So again, while writing the code, there will be two recursive calls, one with the inclusion, one with the exclusion. I'll say that function, the array remains the same. Sorry, just a second. My array remains the same. My n remains the same. My k remains the same. Now, at every recursive call, my index was at this point it was 0, at this point it was 1, at this point it was 2. That I am taking the 0th element, then the first element, then the second element. So my index is getting incremented by 1, index plus 1. Every time I am doing an index plus plus. What I'm saying is index plus 1. Now, I am having two calls. First is of inclusion, second is of exclusion. If I include a particular value, then my sum will also increase by that particular amount. Let's say I'm including that particular value, so my sum will increase to sum of array of k. Is that cool? Now this is for inclusion. This is for inclusion. I'll say I'll have to write the exclusive code as well for the exclusion. Again, in this, my index will also increase by 1, but this time my sum will not increase as I'm not taking this into the consideration. Are you clear with these two function calls? Okay, cool. So now, what I'll say, okay, so what till I did is that I got the function calls I'm having. Now I have to write the base condition. So let's say if my index reaches n, then only I have to stop in here. Right now, I got to know that all of the elements are exhausted, whether I have included it or excluded it. But at this level, all of my elements that I was having got exhausted. So now, my base condition will be having that if my n is equals to index at the last portion, what I'll do, I'll check that if sum is equals to k. If my sum is equals to k, I'll say my result plus plus. If it is not equals to k, this result will not get added. And I'll just simply say return. That's the whole function. So if you write this code, it will tell you that how many number of subsets are there, which are having a um, particular sum, how many subsets are having that particular sum, the number of subsets. Are you clear with this code? Are you clear with this code or do I need to repeat? Okay, you're clear. Okay, so let's try to write down the recurrence relation and find out the complexity. And we'll find the complexity from, again, we can find the complexity from this recurrence tree as well. So for my zeroth level, there is one particular call. For my first level, there are two calls. For my second level, there are four calls. For my third level, there are eight calls. So clearly I can say that it's 2 power n. For any of the n given, there will be 2 power n calls. Let's try to write down the recurrence relation as well. Now, recurrence relation, what it's doing for, this index is getting plus one. If let's say this is array, my index is getting forward, right? So for any of the sub problem, the remaining elements are n minus one. What I'll say is that there are two function calls of t of n minus one. This is a function call that will take n minus 1 elements because one element I have already exhausted, and that second time the second element got exhausted. So for every of the call there are n minus 1 elements left. So there are two such calls, 2 multiplied by t of n minus 1 plus 1. That's for my base condition. So now when I have this recurrence relation of 2t n minus 1 plus 1, try to deduce that it will also come up to 2 power n. You can also deduce using Master's theorem because it is in the form of a n minus 1. This in here n minus 1 b is 1. Okay, so are we good to go? Should we proceed to the next question or should I repeat something? Um, should I proceed to the next question? Cool. Let's say, oh, okay, we will do a variation of this question again. At this point of time, my 3, 1, and 5. I was considering 3 ones, then 1 once, and then 5 ones. Once I'm including it, it got exhausted. Once I'm including it or excluding it, it got exhausted. So let's say I have an array that in which the elements can repeat themselves for a particular subset. What I'm trying to say is that 5 is a valid subset, 5 comma 5 is also a valid subset, 5 comma 5 comma 5 comma anything, any number of fives. So what I'm trying to say is that for any of the particular element, you can take it any number of times. Now, previously, either you have to take it or include it or exclude it, doesn't matter. It will just appear once. Now, 3 can appear any number of times. Let's suppose m number of times. So now I have to go for the same question, that there is some given k, and we have to find out that particular if there is any subset which sum is equals to k, in which the numbers can repeat themselves, and any number of times they can repeat themselves. Are you clear with the question first? um, are you clear with the question? Okay, cool. Now let's say again, at any given point of time, I'm having two choices: to include it or to exclude it. But let's talk about previous one. Previously, even if I'm including, I was doing index plus one. In here, if I'm excluding, my index was also getting plus one in both of the cases. Let's say now I'm including it, I'm excluding it. So if I exclude, I have to exhaust that variable and come to the next variable. I'll say index plus plus. Now, if I'm including it, I will remain at that particular index only. So that in that way, it can repeat that the particular number can repeat itself. So let's say now my base conditions will increase, because I have to check. I cannot just simply say that if my n is equals to k, my index is equals to n, because somehow at this particular, if I'm keeping on including the element, that will proceed to n, go further than n. Now let's try to write down the code for this. What we are having is, we are having some end result. I'm having some function that will take int array, int n, int k, int index, and int sum. Again, I will be having two function calls here, one for inclusion, one for exclusion. Let's say I'm writing for the inclusion first. I'll say my array remains the same, n remains the same, k remains the same. Now, the thing that I just told you, that if I'm including the particular variable, I'll not increment the index. I'll say index. I'll say sum plus of array of k. This is for inclusion. Again, function array n k. If I'm excluding, I'm doing index plus plus, and my sum remains the same as I'm excluding the particular element. So now, are you clear with these two calls? Okay, cool. So let's try to write the base cases we can have. Now, at some point when I am having exclusion, I'm not talking about the inclusion. In the particular exclusion case, that every time excluding, my index will somehow reach to n. So if my index reaches n, I'll check if my sum is equals to k. I'll say answer plus plus, or sorry, result plus plus, and I'll say return as well. This if condition. This is my first base condition. Again, um, let's say if my sum reaches to k at any point, let's say I was, I'll take the recursion tree from the previous question. Now I can repeat the elements. So in this case, I will not be checking for the every level. Maybe I have written that was wrong. Okay, I will be checking in this particular previous question. I will be checking at the only the last levels. Now I have to check for every level because my sum can reach a particular k at any given point of time as my numbers are also repeating. So I'll say if my sum reaches k, what I'll do is that my answer should increment and I should also return. Or else I can have a condition where my sum got greater than k. Let's say for 315, my k being 8, I'll include 3. I'll include 3, the sum will got 6. I'll include 3, the sum will got 9. So now there is no case that if I even proceed further, the sum will come to 8 as it is already exceeded and all of the numbers are only the positive numbers. Sorry, I forgot to mention this particular thing, that in this question every of the array element is positive. This is also a constraint. So now if my sum is greater than k, then I'll simply say return. Are you clear with this code? Basically, are you clear with these base conditions? Others, are you clear with the base condition and this code? I have to go through it again. Okay, I'll tell you. We will go through it again. No issues. Let me take you. So now, what my condition previously was that I can either include a variable or I can exclude a variable. As soon as I do that, my particular element get exhausted. Cool. So every time I'll say index plus plus index plus plus as my element already got exhausted. Now in this case, if I include a particular variable, what I'm saying is that it can repeat itself. It is not getting exhausted. So my current index will remain itself. If I exclude, I'll say index plus plus. That it got excluded, so I have to move further. Accordingly, I am having these two function calls, inclusion and exclusion, in which inclusion my index remains the same and my sum incremented by that particular element, that particular element of the array. In the exclusion, my index got plus 1 and sum remains the same. Now the base conditions. This base condition should be very clear as it is equal to the previous equivalent to the previous case, that if my index reaches n, I'll check if my sum is k, I'll check if result plus plus and return. Now I can get my things exhausted in some other ways as well. If somehow, let's say, I was having 3, 1 and 5 and I am having k is equals to 6. So let's say I'll take the first element 3, then I'll include it at 3. My sum reaches 6. Now, if my sum reaches 6, there is no use of going forward, right? I have already reached my sum. I'll say answer plus plus and return. Let's say my sum was sum 10. Then I'll take 3, I'll take 3, I'll take 3, I'll again take 3. This got me to 12. Now 12 is already greater than 10. Even if I go further, there is no use of doing that, as it will never be equal to 10. It will always keep on increasing and increasing. So I'll just say return in this case. Um, Note down this particular code, then we will try to reduce the complexity. Should I proceed further with the time complexity, or are you still writing? Okay, we'll proceed further with the time complexity for this particular code. Do anyone have any idea? Then you can ping, or else I'll continue. Okay, I'll continue. No issues. Let's say, let's talk about the previous problem. Let's say I was having these particular elements A1, A2, A3, and AN. In the previous problem, to get to a particular sum K, the contribution of A1 was equal to A1 only. That whatever, if it is was 3, it can contribute 3 only, right? Now it can be repeated any number of times until my k is reached. So in previous question, for any of the element, the contribution to reach to a particular sum was equivalent to its particular value only. Now it can be repeated. So now for A1, the contribution can be k by A1, as A1 is getting repeated. A2, the contribution is k by A2. For A3, it is k by A3. For AN, it's k by AN. Are you clear with this? Why I am saying this thing? Because A1, A2, A3, any of the element, it is getting repeated. So its maximum contribution can be the number of times it can repeat itself. The maximum contribution it can be k by k divided by the particular element. So now let's take the sum of this contribution. it will be equal to k 1 by a2 plus 1 by a3 plus 1 by an. This is the contribution sum that what particular element can contribute. Let's say for the worst case scenario, um, what do you think? For a worst case scenario, a element should be minimum or it should be maximum of the particular array. Let's say I'm having 3, 1 and 5. Which one will give me the worst case scenario? The minimum element or the maximum element? Let's say we have one this particular thing. If my a1 will be smaller, will it give the bigger value? Or if it will be big, then it will give the big value. It should minimum, it should be maximum. Great, minimum. Uh, Others, are you clear why it should be minimum? As it is in the divide, if I'll minimize it, then it will produce the maximum result and it will go to the worst case complexity. Uh, you got that, or do you need some more explanation over there? So, in the very worst case, let's suppose my a1, a2, a3, an everything is minimum, is equal to some a1, a2, a3 are equal and they are the minimum elements. So my contribution sum will equal to k 1 by min plus 1 by min plus 1 by min. Let's say in the worst case, every of the element is minimum in the worst case scenario. So it will be k n by min. This will be my contribution sum. Kn by min is my contribution sum for all of the elements. Previously, the contribution sum for all of the element was n because we were having some n elements. Now it is kn by min. So I can say that my complexity is big O of 2 power kn by min. Previously it was 2 power n. Now it will be kn by min. You got this particular point? Please note down the complexity and write it properly with the explanation that why it is worse in the minimum scenario. Then we'll revise what we have done today. Okay, so we will go through the things we have done today and then we will find out. The very first thing we did is time and space complexity, where our time or the space, whatever we are having, is dependent on the input. So now if I am having a code that is looping through n times, then my complexity will be O of n. It will be if it is looping through n times and for every loop there is a loop again, then it will be O of n square. Now one bit tricky part, that if I'm having a nested for loop and a for loop, I mean n square plus n, what we will do is to neglect this n, as this n is negligible when it is compared to n square. Same as for my space complexity. Other thing we discussed was amortized complexity in which we neglect the very expensive but the very rare operations we are having. We just neglect it, and we will for the others, whatever that time complexity we deduce, that will be the total time complexity. After that, we came to recursion. Recursion is a programming paradigm in which we try to deduce that for a particular n, what can be the smaller sub problem. We assume that the function is working for the smaller sub problem as we are expecting. Then we will apply the main logic that for particular nth item which we are on, and we are having the smaller sub problem result as well. We will combine them according to whatever the main logic we are having, and then we will write the base condition. That's how you go for a recursion code. You firstly assume that it is working. Secondly, you have to write down the main logic. Thirdly, you have to write down the base conditions. So we wrote the code for sum of natural numbers, then we wrote the code for factorial, then we wrote the code for Fibonacci. After that, we came to the recurrence relation. Recurrence relation is that finding the time for one element, I mean for the base case. Then we try to find out t of n by using the formulas, and by calculating out the whatever the number of function calls we have. Again, after that, we came to recurrence tree. Recurrence tree, for every of the level, you have to just count the number of function calls you have. After that, you have to sum up every of the number of function calls you got. After that, we discussed the simplified master's theorem. Simplified master's theorem is a theorem that can only be applied to the recurrence relation that are of the type at n by b plus function of n. If any of the recurrence relation is of this particular type or can be reduced to this type, then only we can apply master's theorem for this. So we calculated t as log ba and c as nc of function n. After calculating t and c, we can have three maximum conditions. The first condition is t is less than c. It would produce O of n square. If t is equals to c, it will produce nt log n, and if it is greater than c, it will produce n power t. After that, we wrote the code for Tavora Funai. That was bit difficult and bit tricky. If you have not got it, please try to dry run the code once or twice on your pen paper, or else you will just continue to not get it anyhow. Do it today itself. Then we write the power function, in which we saw that how changing out the smaller sub problems can reduce the complexity. Firstly, we did is to just take the n minus 1, n minus 1, n minus 1, and we proceeded, n minus 1, n minus 2, n minus 3, and we proceeded that way. So our complexity in that case was O of n. Then then what we did is to reduce the complexity by n by 2. So our complexity reduced to log n. After that, we discussed two questions from backtracking. I mean the same question but the different variation. Firstly, in which elements cannot repeat. Secondly, in which elements can repeat. So if you have any questions from any of this, please ask it out, or else we'll bind up today's session. Do we have any questions? Okay. So we will bind up the session here. Thank you.